So now we're going to look at vector multiplication. So the question is, how do we multiply two vectors together? So here's a vector here, let's call it vector A, and there's another vector called vector B. Now the fact that the vector B starts at this point, that doesn't really matter. We could have drawn this vector over here somewhere, it would have been the same vector. But just to make it the more obvious what we're doing, we'll take the vector and we'll actually put it at the same point, okay? So it means that the two tails of the vectors are sitting together. So we're looking for vector A times vector B. So the question is, how do we multiply them? Well, we know a vector has got a magnitude, so you could suggest that in order to multiply the vectors we would simply multiply the magnitudes together. But then what would we do with the directions? How would we multiply in effect this direction with this direction? And does it make any sense to say things like, how can we multiply directions? So there's several different ways of multiplying vectors together, and what we are really interested in is answering the question, what methods of multiplying vectors together are actually useful to us and actually provide us some useful mathematical outcome? Well, the one that we are going to look at now is called the scalar product. So this is one method of multiplying two vectors together. So let's go ahead and we'll look at that now. So in order to do the scalar product, that is multiply these two vectors together, what we do is we say, let us take the component of vector A, which is in the direction of vector B. So we can see what we're going to do here is we drop the perpendicular from our vector A down to our vector B, so this is a right angle here. And this length here is the component of vector A which is in the direction of vector B. So we work out this length here and then we multiply it by this length here, and this is the scalar product. But what is this length here? Well, from simple trigonometry it's going to be A cos of theta. So be sure that you understand where I got that from. Remember that the cosine function just gives you the ratio of the adjacent, so this is this length here, to the hypotenuse, which is this length. So if we call this unknown length here in blue x, we could say x upon A equals cos of theta. Therefore we could say x equals A cos theta. So this distance here is A cos theta. So what we're going to do, we're going to multiply A cos theta with the length B. So let us go ahead and write that out. So we said in order to do this scalar product we have to take the length of vector A in the direction of B. So the length of vector A in the direction B is the length of A, so that's the two little lines here with the A says the length of A. Cos theta will give us the blue length here, and then we've got to multiply it by the length of B, so this is the length of B. So we'll get A dot B, and this dot here is a special dot. This is scalar product is also called the dot product, and the dot there is a particular, if I make it a little bit bigger just to emphasize the fact that this is the dot product. So we're going to have the dot product between two vectors, which is a scalar product, which is A dot B is going to equal to A B cos theta, or the length of A times the length of B times cos of theta. So let's look at an example here. Let's say for example the length of A is 4 and the length of B is 5, and let's say the angle between A and B is 45 degrees. Then the dot product between these two vectors is going to be 4 times 5 times the cosine of 45. Well, the cosine of 45 is 1 upon root 2, so that's going to give us 20 upon root 2, so it's going to give us 10 root 2. So you can see here that the final answer is just a scalar, it is just a number. So it's quite reasonable for you to say, but what does this really mean? We're taking the length of this vector in this direction and multiplying it by the length of this vector, and we get a number. But what does the number mean? And why is that number of any use to us? Well, the usefulness in this scalar product occurs because it tells us how much of one vector is contained within another vector. So let's say, for example, both of these vectors were sitting at 90 degrees. So therefore we'll be able to say, well, there is no component of vector A which sits in this direction. So we'll expect to get the answer 0. And we do get the answer 0 because at 90 degrees, the cos of 90 degrees is 0. So the whole answer there would be 0. So this would then say that at 90 degrees, there's no component of A in the direction of B. But if this vector A was, say, lying exactly on the top of vector B, then the angle would be 0 degrees, and the cos of 0 degrees is equal to a value of 1. So that would mean that the entirety of this vector here would be sitting along in the direction of B. So what's of use or value here is not so much the absolute value here of the answer, it's just the fact that we can use this here in order to tell us whether vectors are sitting perpendicular or whether they're sitting exactly on top of one another. And it also tells us how much of one vector is made up from another vector. So for example, how much of vector A is made up from a vector which is in direction B. So even if your comprehension of this is a little bit sticky, it doesn't really matter for the moment, because the actual application of it is very simple. We just take the length of this vector, the length of this vector, and the cosine of the angle in between, and we multiply them all together, and we'll get the correct answer. So thank you for listening to this video. I'll get you on the next video. Goodbye.